But looking through it, it feels like much more than just, an assignment. It seems like a recipe for building some genuinely practical applications.
Absolutely. And I think our goal here today isn't really to get lost in the weeds of C++ syntax itself.
Yeah,
It's more about pulling out the core concepts, the really insightful bits from this computer science project that, frankly, are useful even if you don't code in C++ or maybe don't code at all.
exactly. Because at its core, what this seems to be about is applying these fundamental ideas, how computers organize information, how they process it to solve, well, actual real world problems.
Precisely.
Okay, so let's dive in then. The first thing that really jumps out is this heavy focus on what they call core data structures.
Hmm.
The project requires students to pick at least two from this quite interesting list. We're talking arrays, linked lists of
Yeah.
things I've heard of.
Yeah, the fundamentals. Stacks, queues, different kinds of trees like binary trees, binary search trees, heaps, which are often used for priority queues, hash tables or hash maps, and even graphs.
It's quite a menu.
It is. And the key thing to grasp is that these aren't just abstract terms from a textbook. They are the essential building blocks for how software actually manages information day to day.
Okay. So there are like different ways to organize stuff.
Exactly. Think of them as different container types. Each one has its own strengths, its own weaknesses, making it better suited for certain kinds of jobs.
Can you give maybe a quick intuitive feel for a couple, like arrays?
Sure, an array is kind of like a row of numbered boxes or parking spots. Everything's in order, and if you know the number, you know exactly where to find something.
Yep.
Very direct access.
Got it. And linked lists, you mentioned those too.
Linked lists are more flexible. Imagine like a treasure hunt. Each piece of information, each node holds its data, but also holds a pointer, a clue, telling you where the next piece of information is. You can easily insert or remove items without shifting everything else around.
Ah, okay. So different ways to connect data.
Right. And the document even touches on some optional, more advanced ones. Things like tries, which are apparently great for like autocomplete features,
Yeah, efficient prefix searching.
and Bloom filters, which are a clever way to quickly check if an item might be in a really large set without guaranteeing it. Useful for certain kinds of filtering.
Interesting. So those are more for specialized optimization.
Exactly, they're optional extras. But that core set, arrays, lists, trees, hash tables, gives you the essential toolkit.
And what I found really cool is how the project immediately pushes you to think about applying these tools. The list of suggested application ideas is huge.
It really shows the versatility, doesn't it?
It really does. I mean, it ranges from, okay, a student record management system
Mm-hmm. Keeping track of enrollments, grades, that sort of thing.
to a hospital patient queue. That seems pretty obvious, like managing who's next.
Right, a classic queue application. First
Yeah.
in, first out.
Then you've got things like implementing Underreader functionality in software.
Stacks often come into play there. Last action in is the first one you undo.
Makes sense? Or a maze solver or GPS navigation.
Graphs are perfect for that, representing locations and the routes between them.
Library inventory, job scheduling, a food ordering system, even social network friend recommendations.
Again, graphs are a natural fit for social networks, nodes are people, edges are connections.
It just goes on.
Hmm.
Sorting algorithm visualizer, airline reservations, file system navigator, music playlist manager, bank transactions, inventory control.
It's quite the list. Timetable generator, online voting, emergency alerts.
Compiler symbol table sounds technical. Autocomplete, we mentioned that. DNS cache, digital wallet, chat application, e-commerce cart, network packet routing.
It really drives home the point that these structures aren't just theoretical. They are everywhere under the hood of the software we use daily.
Okay, so you've got the building blocks, the data structures,
Yeah.
you've got the potential problems to solve these applications. But this project isn't just theoretical brainstorming.
Bad at all.
The requirements, they get pretty specific about the actual building. They're asking for a minimum of 600 lines of C++ code.
Yeah, that's a non-trivial amount. It really forces the hands-on implementation aspect, no shortcuts there.
And they stress using strong object-oriented programming OOP practices. Why is that so important here?
Well, OOP is fundamentally about organizing your code well. Think of it like using well-defined building blocks or objects that group data and the actions you can perform on that data together. It makes the code more modular, reusable, easier to understand, and crucially, easier to maintain and expand later.
So cleaner, more organized code.
Essentially, yes, it promotes good software design habits.
And get this, they can't just grab pre-built versions of these data structures from a library. They have to manually implement at least two of their chosen structures themselves, including all the key operations.
That's right. Things like how to insert a new piece of data, how to delete one, how to update existing data, how to search for something, and even sometimes how to sort the data within the structure.
Why make them do that from scratch? Aren't there libraries for this?
There absolutely are, and in professional settings, you'd often use them. But the point here is deep learning. By building it yourself, you gain a fundamental understanding of how it works internally. What are the challenges? What are the trade-offs in different implementation choices? It's about grasping the mechanics, not just using a black box.
Okay, that makes sense. It's about understanding the why.
Precisely.
And it's not just the data structures. It's the algorithms, too, the methods for doing things with the data. They need to pick and implement at least two sorting algorithms.
Yep. The document lists examples like bubble sort, selection sort, insertion sort, merge sort, quick sort, the classics.
Some probably faster than others.
Oh, definitely. Bubble sort is simple to understand, but usually very slow on large data sets. Quick sort and merge sort are generally much, much faster.
And they also need two searching algorithms, like linear search, binary search. I see DFS and BFS mentioned too.
Right. Linear search is just checking items one by one. Simple, but slow if the list is long. Binary search is much faster, but it requires the data to be sorted first.
And DFS and BFS.
Depth first search and breadth first search. Those are typically used for traversing or searching in tree or graph structures, different strategies for exploring connections.
And again, the key is not just knowing these algorithms exist.
Exactly. They have to be implemented and integrated meaningfully into their chosen application. You can't just tack on a sort function that doesn't actually help the user or the application's purpose. It has to make sense in context.
So it's about applying the right tool for the job within the application they build.
That's the core idea, which leads directly into the next really crucial part: comparison and optimization.
Ah, yes, this looked important. Once they've built their structures and algorithms, they have to analyze them.
Yes, they need to compare their chosen data structures, the two they implemented in terms of performance, specifically time complexity and space complexity.
Okay, break that down. Time and space complexity.
Basically, time complexity is about how the running time of an operation, like searching or inserting, grows as the amount of data increases. Does it stay fast? Does it get slower linearly? Does it get much, much slower?
Okay, and space complexity.
That's about how much memory the data structure uses, again, usually in relation to how much data it's holding.
So it's about efficiency. How fast is it, and how much memory does it hog?
Exactly. And understanding these trade-offs is fundamental. There's rarely one best structure for everything. One might be super fast for lookups, but slow for adding new data, or use less memory, but be slower overall.
They need to understand these compromises.
They absolutely do. And they need to do a similar comparative analysis for the sorting and searching algorithms they implemented. Which one was faster in their tests? Under what conditions? What are the trade-offs?
And they can't just say one was faster.
No, the requirement is to present these findings visually. They need to use tables, graphs, charts, actual data to back up their analysis and justify the choices they ultimately made for their specific application.
So evidence-based design.
You got it. It's about making informed decisions and being able to defend them.
Which ties nicely into the next major section: documentation and professional presentation. This isn't just about coding, it's about communicating the work.
A vital skill. They need to produce a pretty comprehensive project report, typically as a PDF.
And looking at the required components, it's quite thorough. Introduction, objectives, detailed descriptions of the data structures and algorithms used.
An implementation overview, potentially with code snippets or screenshots to illustrate key parts.
They even need a UML class diagram. What's that exactly?
It's essentially a visual blueprint of their software structure. It shows the different classes or components they've built and how they relate to each other. It gives a high-level overview of the system's architecture.
Okay. And then, of course, that performance analysis we just talked about needs to be in the report.
Absolutely. Summarizing their findings on efficiency. They also need to detail who did what in the group member contributions.
Accountability.
Yeah. And provide links to their project hosted on GitHub and a summary post on LinkedIn.
Ah, GitHub and LinkedIn. So public-facing elements.
Definitely. GitHub is the standard platform for hosting and sharing code nowadays. LinkedIn is for professional networking and showcasing your skills and projects.
And the report wraps up with a summary, conclusions, and maybe ideas for future improvements.
Right. Standard practice for project documentation.
But it's not just the report document itself. They also have to actually publish the project on GitHub.
Yes, with a good repository structure and a clear readme file explaining what the project is, how to run it, etc., making it accessible and understandable to others.
And that LinkedIn summary, is that just a link or something more?
Usually a short post summarizing the project, what they learned, maybe highlighting a key feature or challenge. It's about professional visibility.
And then the final submission is through their usual online platform, like Google Classroom.
Correct. Formal submission channel.
This focus on GitHub and LinkedIn feels very current,
Yeah.
very relevant to actually getting a job or working in the field.
It absolutely is. It bridges the gap between academic work and professional practice. Building a portfolio, learning to communicate your work, it's incredibly valuable.
Makes sense. Now, to really understand what success looks like for this project, the document includes a detailed evaluation rubric.
Always good to see how things will be graded.
It tells you what the instructors are really looking for. And what stands out immediately is the weight given to just functional code. Does it work? Is it well structured?
That's often the biggest chunk of marks in programming projects. It has to run correctly.
And right alongside that is the implementation of the operations on the data structures, the quality of the OOP design.
Yep, the core technical skills.
And significantly, the comparison of the data structures and the analysis of the algorithms.
So it's not just coding. The analytical part, understanding the why and the trade-offs, is clearly weighted heavily too.
Exactly. It reinforces that they need both the practical implementation skills and the theoretical understanding.
Then there are marks for optimization efforts, the quality of the GitHub repository, the LinkedIn post, the project report itself.
Right, the whole package. Even creativity, innovation, and the overall presentation get factored in.
So they're looking for well-rounded projects, not just code that compiles.
Yeah, definitely the whole picture. And finally, there are a few important notes at the end. One is about collaboration
Emphasis on equal contribution within groups.
and the possibility of oral assessments or vivas. Basically, they might have to verbally explain or defend their work individually.
Keeps everyone honest and ensures individual understanding. You can't just hide in a group project.
And speaking of honesty, there's a very clear, bolded, zero-tolerance policy for plagiarism.
As there should be. The point is to learn by doing, not by copying.
Absolutely. And one last little carrot. The potential for outstanding projects to be recognized publicly.
That's a nice touch, a good motivator to really push for quality and maybe do something a bit innovative.
Definitely. So, okay, we've walked through this quite specific C++ project structure. But stepping back,
The underlying principles are universal.
that's exactly what I was thinking. This whole process, identifying a problem, choosing the right tools, data structures, designing efficient procedures, algorithms, implementing them, testing them, analyzing their performance, and communicating it all clearly. That's applicable way beyond C++ part.
Absolutely. It's fundamental to software engineering, yes, but also to problem solving in many technical fields and even just thinking logically about efficiency in general.
Understanding these concepts, even at a high level, gives you a much better appreciation for how the software you use every day actually works, why some apps feel snappy and others feel sluggish.
Right, it demystifies things a bit. You start seeing how complex tasks are broken down into these organized steps and managed using these different data containers.
So maybe a final thought for everyone listening. We've seen how central organization and efficiency are in this coding context. How might those same concepts, thinking about the best way to structure things, the trade-offs between different approaches, the need for clear processes apply to challenges in your own field, or even just in managing your daily life?
That's a great question. It's worth pondering how these fundamental ideas might pop up in unexpected places.